Okay, why don't we get started then? Welcome to the webinar, 7 Steps to an Effective Alarm Management Program. My name is Todd Stauffer. I'm the Director of Alarm Management here at Exida. You all will be on mute during the presentation. If you have questions that arise, please either write them down or enter them into the questions box on the GoToMeeting control, and then we'll try and address them at the end of the presentation. So my focus at Exida is on alarm management. I've been involved with the creation of the standard that was created in the US, ISA 18.2, involved in the creation of that standard since 2005, so I'm an editor and voting member for that committee. I've also been involved with the creation of some of the subsequent works, technical reports that provide more details, and I'm currently the co-chair for a new standard development on safety controls, alarms, and interlocks. Now, Exida is the premier company for functional safety, alarm management, and cybersecurity. We focus on personnel and product certification and assessments. We've done more product certifications of SIL equipment than any other company in the world. We also have a suite of tools for safety system design and engineering, operation and maintenance. And as part of that, we consider SIL Alarm, which is our alarm rationalization tool. We consider that to be a part of the SIS design suite, because we do consider alarm rationalization to be an extension of the functional safety lifecycle. We are a Rockwell Encompass partner and also an Emerson Alliance partner for alarm management. So why don't we get started with the webinar then? So the purpose of this webinar is to talk about how to create an effective alarm management program, one that has continuous improvement, one that allows you to establish your initial baseline via some benchmarking, that helps you identify and address issues, that delivers continuous improvement, and also provides a way to maintain the integrity of the alarm system. In addition to that, before we get started with that, we'll go through some of the key alarm management practices and principles. Now, as part of this, many of the examples, we will talk about specific functionality of different control systems, because that's important to know to understand what you can take advantage of to make the most in your alarm management program. So we will have specific examples from different DCS platforms, including Emerson DeltaV, Rockwell PlantPAx, Honeywell Experion, Yokogawa Centum, and Siemens PCS 7. Let's start with a discussion of what the purpose of an alarm is. In general, the process automation system will keep the process in the normal operating range, and at certain points when it gets outside of that range, we'll call it in the abnormal situation area, that's when we need an alarm. And we want that alarm to go off to tell the operator, hey, I need your attention, I need you to take corrective action, and I need you to take that action relatively quickly to prevent an impending consequence. If the operator does that and performs the corrective action appropriately, then the process will turn around and go back from the abnormal situation area into the normal operating range, and the alarm will clear. If, however, the operator does not respond effectively, the process variable will continue to escalate until a consequence occurs, such as a shutdown of the safety system. So the purposes of an alarm also include keeping the process within normal operating limits. That would be keeping it in the green zone. And another way to think of it is alarms are also there to keep the process out of the red zone, out of the shutdown zone. Now, the scenario that we talked about with an alarm, it occurs, the operator responds to it, the process is corrected, the alarm clears. That's the way it's supposed to work. But if you go into your typical control room and we look at the alarm summary display, we'll often see tens to hundreds of alarms displayed that scroll down and fill the page with alarms. And they may have been there for days, weeks, or months. So they're obviously not following the purpose of what an alarm is supposed to do. That's an example of a stale alarm, which gets in the way of the operator. Stale alarm is just one type of alarm management issue. Let's look at a couple more. We would be concerned about operators getting too many alarms, whether it's a steady state scenario or whether it's after an upset, and we'll call that an alarm flood. We also should be concerned about nuisance alarms, alarms that are presented to the operator where they don't need to respond for one reason or another. Stale alarm is one example of a nuisance alarm. And then scenarios where the alarm priority is not meaningful in helping the operator understand the relative importance. If you have these kinds of problems in your system, then unfortunately you are robbing the operator of an effective tool or an important tool to help them do their job. The alarm system is critical for the operator to be able to do the best job that they possibly can. Let's take a look at part of why that is. The key to operators performing well is to maximize their situation awareness. So what is situation awareness? It's the ability to take the external cues of what is happening in the process, including alarms, and understand what they mean now via the mental model, the understanding of the process. So what they mean now, what those cues mean now, and what they will mean in the future, or what that means to what is going to happen in the future. So you can imagine that if these cues are false alarms, or are not meaningful, or mean the wrong or incorrect things, what's going to happen to the operator's situation awareness? It's really going to be compromised. And it will be very difficult for them to truly understand what is happening with the process, to do the best that they can, and to not make mistakes, frankly. If they're getting incorrect signals as to what is happening in the process, it's not hard to see that they might make a mistake because they've been given false information. Another element that I wanted to point out and talk about were alarm floods. This is a scenario where the operator gets more than 10 alarms in 10 minutes, so it's a very difficult and challenging situation. That's generally speaking too many alarms to be able to respond to on a consistent basis. So it is very possible that the operator may get so many alarms that they can't understand and respond and process them all. So they could very easily miss one or more of those alarms, and if they were critical, it could ultimately lead to a shutdown or some form of consequence. Now, one of the other reasons that alarm floods are so dangerous is that they're very much associated with plant upsets, which are very stressful times for the operator. And if you're involved in the functional safety world, you'll recognize some of the metrics that are shown down here, which are some representations of the probability of failure, the likelihood that the operator may not be able to perform their role successfully. What I want to call out is how much the operator's ability to perform successfully is compromised under stress. You can see there's orders of magnitude change in their performance, orders of magnitude change in the likelihood of making a mistake. And alarm floods and the associated upset that go with them are definitely stressful situations that would potentially compromise the operator's performance. So that's why we want to launch into an alarm management program. Now, the guidance for that program will be the standards on alarm management. In the US, the relevant standard is the ISA 18.2 standard, first released in 2009, updated in 2016. It was actually used as the basis of the international version of the standard, IEC 62682. Now, the two documents are very similar. I would say 80 to 90% of the content is the same. They both contain requirements and recommendations for what needs to be done. They both contain the same alarm management life cycle, and that's what we see here on the right-hand side. This is essentially the alarm workflow practice. And what we're going to do is to essentially create an alarm management program out of that alarm management life cycle, or that conforms to that alarm management life cycle. We will use that as the basis. One of the other things that the standards do is they define the definition of an alarm, or the criteria for what an alarm is supposed to be. So let's look at that. An alarm is supposed to be an audible and/or visual means of indicating to the operator, and I've underlined the word operator to point out that the operator is the target audience for the alarm system. Second part of the definition is that an alarm needs to indicate an equipment malfunction, process deviation, or other abnormal condition. I have the word abnormal condition underlined to indicate that an alarm is supposed to indicate that something is wrong, something unexpected has happened. And then last but not least, an alarm requires a timely response. More than acknowledging the alarm or silencing the horn, we're talking about opening a valve, turning on a pump, something that will actually correct the process abnormality. Now, there's a process that we're going to talk about in a little bit called alarm rationalization, and that's essentially the review of the alarms that you have configured or that you propose to make sure that they all conform with this definition. If you have an alarm system that has performance issues, it is likely because many of the alarms do not meet this criteria or this definition that we see here. Now, one of the other reasons why folks have alarm management issues is they oftentimes use the alarm system to communicate everything that the operator needs to know, whether it's a true alarm or not. Part of what we want to do from a human factors point of view is to make it so that the alarm summary display, which is used for display of the alarms, contains only true alarm conditions, something that requires operator action and represents an abnormal situation. Now, that's not to say that these other types of notifications, alerts and prompts and messages and status indications, are not important. They are important as well, but alarms are more important. And the idea is that we want alarms to be separated out from these other types of notifications, so that when an alarm comes in on the alarm summary display, the operator doesn't have to question, for example, whether they need to respond to it or not. By definition, by the fact that it is an alarm and all the non-alarms have been removed, they would know that they would need to respond. Now, part of why this is important to talk about is more and more control systems actually allow you to do this separation of these notifications within the control system. This is an example of a Honeywell system where you can see that alarms can be clearly differentiated from alerts, messages, and system diagnostics, just as what we saw on that table. So now let's turn our attention to how do we create that effective alarm management program. We saw the alarm management life cycle. Sometimes it can be a little confusing or challenging for folks to know where do I start or how do I drive action from that. So what we've done is kind of simplified it to create a 7-step process. The first step is to actually benchmark your initial performance. And that actually consists of, or is the same as performing the monitoring assessment step and the audit step of the alarm management lifecycle. But during this step of our 7-step process, we are measuring the alarm system performance to see how many alarms the operators are actually getting, how many nuisance alarms, that kind of thing. We're also doing interviews to find out how well the alarm system works for the operator. and then we'll use that information to help us create an alarm philosophy document, which is the general guideline for how to do alarm management at your site. All things alarm management, whether it's configuration or processes and procedures. Once that's done, once the initial starting point steps are done, then you're ready to go into the continuous improvement portion of the process, and that begins with alarm rationalization, the review of the alarms to make sure that each one is actionable by the operator and has a purpose warranting it being enunciated to the operator. After rationalization is complete, we want to make sure that we push the updated values into the control system and that we implement alarm response procedures. These are aids to the operator to help them know how to respond to the alarm. Now, in some cases, just performing alarm rationalization may not be sufficient to get rid of all of the alarm problems. So there may be another step required called advanced alarm design, which might involve implementing alarm suppression, for example. Sometimes this is referred to as dynamic rationalization, whereas the first pass of rationalization is referred to as static rationalization. And after that is done, then we launch into the, again, measuring our alarm system performance. And this is how we set up our continuous improvement loop. So perhaps on a monthly basis, we measure our alarm system performance, see how we're doing, whether we're making things better or worse, identifying the currently worst performing alarms, which are then identified to go through the alarm rationalization process and get fixed. So you can see this becomes a continuous improvement process, and it's an ongoing process. The last step in the program is to perform audits. This is a way to make sure that you're following the processes and procedures that you said you would in your philosophy document, and to make sure that the values of the alarm settings that are actually running in the DCS match up with what you defined during rationalization in your master alarm database. So it's maintaining the integrity of the alarm system. So the whole purpose of this alarm management program is to make the alarm system back into an effective tool for the operator to deliver situation awareness so that they can better prevent unplanned shutdowns and damage and any kind of process safety incidents. Now, one of the key takeaways from this webinar hopefully will be understanding the alarm management functionality that's provided by the different control systems. With the modern DCS, there is a lot of advanced alarm capability built in. And I would very much encourage you to, if you have a running control system, to learn what capability is available. I would be willing to bet that there are alarm management functions that either you do not know about or have not implemented to their fullest extent that could help you solve some of the issues that you have. So hopefully this will be an introduction to some of those features, prompting you to go find out more. Let's take a look at an Emerson DeltaV system. Now, to comply with the alarm management lifecycle and to create that alarm management program requires the use of some alarm management tools. We have an alarm philosophy template that we can use to help folks create that alarm philosophy document. I mentioned our SIL alarm tool earlier. That can be used for alarm rationalization and act as the master alarm database. Then the DeltaV system itself has very powerful alarm management functionality built in and available as options. So it's definitely worthwhile understanding what is available: conditional alarming, alarm suppression, alarm shelving, alarm flood suppression. So there's a lot of capabilities there that can be taken advantage of. Now, one of the key parts to any effective alarm management program is this monitoring and assessment step. And pretty much you need a tool to do that. This is where we measure the actual alarm system performance, like looking at months of data at a time and calculating our KPIs. In a DeltaV system, this is performed by DeltaV Analyze, which can be supplemented by Cytex Excel Reporter for custom reports. To support management of change and maintain the system integrity, the SIL alarm tool can be used there, as well as DeltaV version 13 provides some runtime audit reports as well. Now, looking at some of the other platforms, the Rockwell PlantPAx system also has a lot of powerful alarm management capability built into it. You see some of the specific functions and examples identified here, and a tool to perform the monitoring and assessment. Looking at the Yokogawa Centum system, also capabilities available with the system to perform powerful alarm management functions for shelving and such. That would be the CAMS tool. And then there's also functionality provided by the exida suite of tools. This is just one example of what could be used with the Yokogawa system. There's obviously other products available from other suppliers that could be used to fill these roles as well. For a Honeywell system, Honeywell provides capabilities and tools to meet these different functions. They have a tool called the Alarm Configuration Manager, which can act as the master alarm database. They also have alarm help and shelving and other capabilities, as well as a tool for performing the alarm system measurement called alarm and event analysis. So you can see that every control system kind of has their version of how to do different things, and it's continuing to innovate. Each year, the suppliers are adding new capabilities to comply with the alarm management standards and to make things better. So it's definitely worthwhile understanding what's available so that you can take advantage of it. So now let's talk about how to actually crank through our alarm management program. Let's start with the first two steps, really the getting started portion of the program. And here we are benchmarking the alarm system performance. That's what you would do if you were a brownfield. So this webinar applies to any different type of control system, as well as both brownfield and greenfield applications. So if you're a brownfield application, you start with the benchmarking step. If you're a greenfield application where you don't have a system up and running yet, then you would move directly to the alarm philosophy development step. Now for the benchmarking, we do need a tool to measure the alarm system performance and compare that to what's in the alarm management standards. Here we see the metrics from the ISA 18.2 standard. So we have metrics defined for the number of alarms that the operators should get per day, the amount of time the system is in an alarm flood, the number and type of nuisance alarms, the priority distribution. So what we want is a tool that can calculate the actual performance of our system so that it can be easily compared to what's in the standard. Example, the number of alarms per 10 minutes, alarm flood conditions, top 10, and priority distribution. So we want a tool that can automatically calculate those KPIs so we can see where we are in relation to the standard. This will help us know how urgent it is to get this alarm management program started. It also serves to document our starting point for the alarm management journey. Another portion of the performance assessment is to document or determine alarm issues. So one area of issue is with bad actor alarms. What you'll find is in many systems you may have some 10,000, 20,000 configured alarms, but there's 10 or 20 of them that contribute the majority of the activity, and not in a good way. So here we identify our top 10 bad actors, and we can see for this system, these 10 modules produced over 50% of all the alarms for the operator. So there's obviously something wrong with these alarms, which we'd want to understand so that we could fix them, not only these individual cases, but if there's systematic ramifications of that, we definitely want to know that. Now, some people ascribe to the fact that the very first step, or believe that the first step is just identifying the bad actors and fixing them piecemeal. I personally believe that the bad actor identification and resolution should be included as part of the rationalization. So it's important to do, and it's beneficial to be done, but it should be done as part of the rationalization, not as an isolated step that you do before entering into a true alarm management program. Now that will document quantitative metrics. We also want to do qualitative assessments, determining how well the alarm system is working for the operators. There's many things that can be measured by a tool, but there are some things that you can only find out by talking to the operators themselves. Things like whether they understand the alarm messages that are presented to them and whether they know what to do when each of the alarms occur. That's important information to assess to help identify areas that need to be improved and to identify systematic underlying issues, such as this one, where in an actual audit, we found that approximately 50% of the alarms the operators said that they got were pretty much only for information. Then they didn't require an actual action. And based on the definition that we looked at earlier, we can kind of see that that's not what an alarm is supposed to be. So potentially 50% of the alarms need to go away or have something different done. But what we also identified here, or what the operators identified, was a systematic problem with change from normal alarms that would go off anytime the operator took an action. And that was the way the system was designed, and there were hundreds of those alarms. And they clearly pointed out that that was not needed, and that was an opportunity for improvement. So that's fantastic information to have and to get before you launch into the development of an alarm philosophy document, which should give you the guidelines for how to do alarm management at your site. Now you can see the content that's required or expected. This is what's defined in the ISA standard as what you should have in your alarm philosophy. If you have only seen the old version of the ISA standard, I would encourage you to check out the 2016 version, as it adds 4 new areas to go into an alarm philosophy. They're highlighted at the bottom here. And 2 of them are actually, well, they're all important, but and we're going to talk about 3 of them during this presentation. So it's obvious that they really are important, and that is the auditing process, creation of alarm response procedures, and alarm shelving. So as part of the alarm philosophy creation process, one of the things we want to do is define criteria for determining whether an alarm is valid or not. And we can use the definition of an alarm to create criteria, such as what we see here. And the idea is that we want to create some criteria that can be applied simply and consistently to help folks quickly and easily determine whether something is a valid alarm or not, or is not a valid alarm. This will help eliminate the alarms that are for information only. It would help us categorize something as not an alarm, but perhaps an alert or a prompt or a message. But you can see hopefully that if you were to apply this criteria, it would help you eliminate some of the alarm management issues. We also want to define how to prioritize alarms. Alarm priority is what the operator should be able to use to determine the relative importance of an alarm, or to assess the relative importance, to help them know which alarm to respond to first. In a typical control system here, like a DeltaV system, there would be approximately 3 different process alarm priorities. There's really no need for more than 3 or 4 for the operator. And the idea would be the highest priority, in this case called critical, there'd be no more than about 5% of all the alarms would have that critical priority. That means they would really stand out, and they would be few and far between. Now, we need to figure out next, how do we actually determine the priority of an alarm? And what's recommended is to develop a methodology that takes into account the severity of the consequences. So how bad would it be if the operator didn't respond? And we will evaluate that in a couple of different areas, and the amount of time that's available to the operator to respond. And we can see an example down here in the right-hand corner. We have a consequence matrix for evaluating or ranking how bad the consequences are in different impact areas. We also have our time to respond thresholds for use in determining what the priority is. And the idea is once this matrix is applied, from now on, when you have the critical priority and an advisory priority at the same time, the operator knows that they should respond to the critical priority alarm first. And you can see there's truly a reason why, because when we look at the potential consequences of a critical priority alarm, it could be much more significant than an advisory priority alarm. So to drive the response in the operator that we want, we use this priority differentiation. Now, one of the other things to address in the alarm philosophy is how to deal with scenarios where alarms are not working, or there's nuisance alarms, or are challenging alarm system scenarios. So this could be where a transmitter is connected to the DCS and it's in alarm, but it's not yet commissioned. So how do you deal with that situation today? Many people would just leave that as a nuisance alarm and it would become a stale alarm until it's commissioned. Well, we can do better than that now. We can do better in that when it comes to malfunctioning hardware as well. Scenarios where the alarm and the hardware require maintenance. How do you deal with that today? How do you deal with alarms that are part of hardware that's being tested or calibrated? Or when an equipment or a unit is idle, is not being used, or is offline for maintenance and is generating alarms that are not meaningful at that point of time. Or after an equipment trip when the operator is flooded with alarms, or just nuisance alarm scenarios. If you think about how you handle those scenarios today, in many cases, people are not doing anything special and they're making the operator just ignore the fact that there are stale alarms or nuisance alarms. And that makes it hard for the operator to concentrate. It ruins their situation awareness. So what we want to do is think about how to use the features in the modern DCS to do better than that, to make it so the operator can retain or keep their focus on the most important things and not get distracted by a nuisance alarm. So the way to do that is through the implementation of alarm suppression. And suppression is defined in the ISA standard as basically preventing the indication of the alarm to the operator when they don't need to see it for whatever reason. And there are 3 different types of suppression. The first type is called design suppression. That is when the system automatically detects the status of the process in the plant and then suppresses the alarms that the operator does not need to see when you're in that state. The second type of suppression is called alarm shelving. This is like the snooze button for the operator. It's a way for them to safely and securely suppress an alarm in a way that it doesn't get forgotten about. It will come back. It is only temporary. And then the third type of suppression is called out of service. This is when the alarm is suppressed indefinitely for reasons such as maintenance, for repair and replacement. So one of the important things is to talk about alarm shelving, whether you will use that or not and how you will use it. I've spoken with many end users that are hesitant to allow their operators to shelve alarms. Well, I believe that there is a time and a place for shelving, particularly if you have nuisance alarms. So during the development of your philosophy, you should think about when it's okay to suppress alarms. Under what circumstances and for what alarms. You may decide that for your highest priority alarms or alarms that are related to safety, that they should not be able to be suppressed. And that would be fine if that's what makes sense from an operational point of view. But I do think it's important to be able to put this tool in the hands of the operator. It's actually a required function now of a DCS to be able to provide shelving capability. That was a new requirement that was added when the international standard came out. And here we see an example of a DeltaV system where for each individual alarm, we can set the maximum time that the alarm is shelved or suppressed. So depending upon the type of the alarm or its usage, you could set the shelving time for 12 hours or 8 hours, one shift. You could set it for 1 hour, or you could set it for all zeros, which would prevent the alarm from being able to be shelved. So you can systematically define the shelving ability of each alarm. We also want to make sure that the status of the alarm is visible to the operator within the HMI, and that there is a list or a summary of all the alarms that are shelved. And that list becomes pretty important because that should be something that operators are looking at as part of their normal routine during shift handover. So when they first start up their shift, to look at which alarms are shelved or suppressed so they know that going forward. Now, continuing with the example of a DeltaV system, understanding the differentiation of shelving, which is the operator temporary suppression function, and the out of service function, which is the long term for maintenance, the way that's actually implemented in a DeltaV system, there are two different functions for that. And you can set up different access and control privileges so that operators have the ability to shelve an alarm, but not to take it out of service. And that would be reserved for a maintenance role or a supervisor role or an engineering role. You can also require that an operator indicate the reason for when they suppress the alarm. Honeywell has a similar implementation of alarm shelving, similar but different functionality. So one of the key takeaways I hope that you see is you need to understand the functionality that's actually provided by the DCS before you dictate the requirements and a philosophy, because you may find that some of the things that you want to do you can't, or that you're not doing or not implementing or not leveraging the functionality that is provided. So in a Honeywell system, the operator actually gets to determine how long the alarm will be shelved for based on their selection of the reason for shelving. So different application, but again for the same function, alarm shelving. In a Yokogawa system, alarms can be shelved for lengths of time between 1 minute and 24 hours. Now, the way this is set up, in the CAM system, each alarm has the ability to be enabled or disabled for shelving purposes. And then in the configuration, we set up different shelves. And each shelf has a different shelving algorithm, whether it's a one-shot or continuous, and it has a different maximum amount of time to be on the shelf. So it could be 1 hour, it could be 8 hours, could be 12 hours, as well as different access control privileges. So we could set up a shelf that's 24 hours, and that would only be for maintenance or supervisor, and 1 hour that would be for operations. So that's how it works in a Yokogawa system. Now moving on to another part of the philosophy, defining alarm classes and classification. Classification is a way to group alarms that have common sets of requirements for things like training or testing or management of change. Examples include alarms that are for personnel safety or are safety-related alarms or for environmental purposes, or are associated with alarms that are called out in a layer protection analysis used as an independent protection layer. But the whole purpose here is to ensure that alarms that have higher importance get treated with more rigor, or the appropriate level of rigor. And one of the ways that that is differentiated is by the use of a concept called highly managed alarms. So whatever classifications you define, you can select 0 or 1 or more of them to be designated as highly managed. If they are, then there is a specific set of requirements, a prescriptive set of requirements that must be met as defined in the ISA standard. So let's think about where that might be useful. And the alarms associated with a building that could have low oxygen, such that if the alarm indicating that didn't work and someone walked in there, there could be a fatality. That's a pretty serious and important alarm, and we would want to make sure that that alarm is tested very frequently, is not disabled without significant management and change review. So you can see that the processes for managing what happens with that alarm would be significantly different from your average process alarm, and that's what classification's for. So now we're ready to move into the performance improvement part of the program, starting with alarm rationalization, where we review the alarms to make sure that there's a true purpose for the operator to see them, and we document the results. Now, there is a process defined in the technical report number 2 from ISA 18, and it basically entails a number of steps, which we'll take a look at some of them, but the idea is this is a process, a repeatable process that will help you determine the need for an alarm, the importance, its design information, its alarm limit, its priority, etc. And then you document that information in what's called a master alarm database. So if we look at the first steps of rationalization, the determination of whether the alarm is valid or not, by looking at what is the consequence if the operator doesn't respond, what are the likely causes, what's the corrective action that the operator is supposed to perform. These are the key things that we need to think about to validate that the alarm is even needed, and we may also want to document the confirmation. So in this case, alarm rationalization becomes a knowledge capture process. If your most senior operators are taking part, then you are essentially documenting what they would do when the alarm occurs. If you document it in SOAlarm, then you can turn that into an alarm response procedure, an aid to the other operators that can be presented when the alarm occurs. And that can be a PDF that's called up, or many DCSs now can provide a window into that information, in some cases called alarm help. And here you can see the example from a DeltaV system, where we can actually take the information from rationalization and push it into these alarm help faceplates automatically, which means now when that alarm occurs, every operator, no matter how long they've been at the plant, gets the benefit of seeing what your most senior operator would do. So it's definitely an important activity to think about in conjunction with rationalization, and that is taking the outputs of rationalization and creating alarm response procedures. So now let's look at some of the other steps from rationalization. We prioritize the alarm. We assign the ranking of the different consequence assessment areas, the amount of time to respond that determines the priority. We also review or document or determine what the alarm limit should be, and we're essentially trying to set the alarm limit in relation to the consequence threshold, which is the value of the process variable where the consequence occurs. So we can document that. We can document process dynamics associated with this, and we can use that to make sure that the operator has enough time to respond from when the alarm occurs to when the consequence might happen, or the last point in time before they can prevent the consequence. So we can document that within the SOAlarm tool. And what's also important during rationalization is to document your rationale for why you set the alarm limit where you did, so that if someone wants to change it later, you can validate or evaluate whether that change is warranted or not. Another thing to determine or document during rationalization is scenarios that would result in consequential alarms, such as a low discharge pressure alarm on the outlet of a pump. That alarm will occur anytime the pump is shut off. So knowing that, during rationalization, we could document the fact that we want to make that alarm a little bit smarter and not have it just enunciate based on the value of the pressure, but also based on the status of the pump, whether the pump is running. So we only want that low alarm condition to occur when the pump is running and the pressure is less than the low limit. When we're all done, we've come up with and documented the design of the alarms that are necessary in the master alarm database. And here is the listing of what's expected and what's required to have documented as a result of rationalization. And that is in your master alarm database, which could be the SIL alarm tool, it could be an Excel spreadsheet, it could be an Access database, it could be a piece of paper. There's also other tools on the market for doing that. And the benefits of rationalization, and part of the reason why you have operators take part, is so that they can see the changes that are being made and they can adjust the way they treat the alarm system. So they realize that no longer can they ignore the first alarm, expecting the second, third, or fourth and waiting for them before they respond. They will realize that, hey, we're only going to get one notification now, so we need to no longer ignore alarms. We need to respond the first time the alarm occurs. Then that results of rationalization need to be pushed into the control system so that the changes take effect. In our SIL alarm tool, we can export that alarm information for taking into the control system, in this case the example being a DeltaV, and update all those parameters, including building those alarm help displays. Now, the alarm response procedures, why would we want to create them? Well, if you put yourself in the shoes of a new operator, what would you want to know when an alarm occurs? You would want to know what has happened, what's going to happen if you don't respond. You'd want to know, what should I do? How much time do I have to respond? Things like that. How do I validate that this alarm is real? Those are the same things that we think about and talk about during alarm rationalization. So if we can document that, that becomes, again, very useful information to turn into an alarm response procedure. And here you can see an example of another alarm response procedure format, in this case for a Rockwell PlantPAx system. Now, on this screen, we're showing the actual requirements for what's supposed to be in an alarm response procedure. This is from the ISA 18.2 standard. And on the right, we can see Honeywell's implementation of an alarm help faceplate. Again, a lot of valuable information potentially for the operator. In this case, the information is coming from their ACM database for display. So rationalization and implementing alarm response procedures will address many problems. However, alarm floods are very different from many of the other nuisance alarm type issues. And you may find that just performing that first rationalization, we'll call that a static rationalization, is not sufficient to address alarm flood scenarios. So we need to go back and do, in some cases it's called a dynamic rationalization, or we'll implement alarm flood suppression. So you want to look at what tools are available within the control system to help you identify when you're having alarm floods and helping to understand what's happening, the causes and the effects, so that you can then address that either through creation of alarm flood suppression schemes or using tools to look at statuses and update alarm statuses. So for a DeltaV system, as an example, when you are done your alarm rationalization and you're going to come back for your second pass, your dynamic rationalization, to suppress alarms during a compressor trip event, we can, in the SIL alarm tool, define our trigger conditions for when that suppression should take place. We can define what alarms should be suppressed. We can define a common alarm. So everything about the operation or running of that suppression scheme or that suppression group, and then that can be created automatically within the DeltaV control system so that it runs actually in the controller, and also creates faceplates and status displays to indicate the status of the alarm suppression scheme. So what alarms are suppressed, what conditions have been satisfied to cause that suppression, so that the operator always has visibility into what alarms are suppressed. We would not want to have alarms being suppressed and the operator not know about it or not realize that there are alarms that are not there because of that suppression. Now, there's other ways of implementing suppression with other tools and in other control systems. Here's an example for a PCS 7 system where we're implementing the suppression in logic in the control system as well, detecting the state and using a unique function block or chart called a state rep block to indicate whether the state is active or not. That information can be used in the engineering system to say that when we are in a given state, such as the compressor has tripped, we can indicate whether the alarm should be hidden or whether it should be presented to the operator. So on an alarm by alarm basis, given the state that is detected, whether the alarm should be suppressed or not. Now that can be used for upset scenarios like alarm compressor trips, as well as for expected scenarios like you are starting up the process or you are shutting down a unit. So that can be used for both. So now the last step in the performance improvement part is to measure your actual performance on an ongoing basis. So for example, monthly, you would want to perform the function to generate your alarm system KPI reports. How many alarms are the operators getting? Are you increasing or decreasing as a function of time? Hopefully you're reducing that. As well as there are many other reports that ideally you'd have the tool create automatically for you and email out to the people that need to look at it. So we're going to generate our KPIs, but we're also going to generate detailed reports to help us dive into events and understand scenarios to diagnose issues and fix them. So again, this is how we create a continuous improvement loop by identifying, in this case, chattering alarms, which would then be taken back to the rationalization process to review their design to see whether it just requires a simple implementation of a deadband or an on-off delay, or whether the alarm limit is totally set in the incorrect spot, or that the alarm is not even needed at all. So this portion of the program identifies alarms that need to be fixed, and we cycle back to that rationalization step. So another diagnostic would be stale alarms. Now for some performance assessment tools, a bonus is if the metrics can be calculated based on particular alarm classes or alarm classifications. It may be reportable to authorities the number of alarms or the instances of alarms that relate to environmental exceedances, for example, or safe operating limits exceedances. You may want to know the activations of your LOPA alarms to validate your LOPA analysis, your initiating event frequency, for example. So if your performance monitoring tool can calculate the metrics based on class, that can give you a very different slice or look into the control system performance for those particular really type of critical alarms. And the last step in the program is to verify or maintain the alarm system integrity. So one of the steps in there is to validate the processes that you're using and the procedures to make sure basically that you are doing what you said you would do. So if changing of an alarm limit requires a management of change activity be followed, then you want to verify that that's actually what's happening. And if it's not, then you want to investigate why so that it can be corrected. And the correction could be an update to the alarm philosophy to say, hey, we can't do this or we don't want to do this anymore, so we update the philosophy. Or it could be, hey, we need to train people better on what the process is or what's expected of them when they want to change the alarm limit. So again, this is a way to help maintain the integrity of the process. Now for maintaining the integrity of the alarm system configuration, that's where we want to do some audits of the alarm system configuration, the actual values of the alarm parameters that are running in the DCS versus those that are in your master alarm database, representing what you came up with from rationalization. So we want to make sure that after you've put all this time into establishing what alarms should be enabled, what their priority should be, what their limits should be, that those aren't being changed without proper authorization in the control system. So an audit, such as using SIL alarm as we see here, will identify any changes in alarm parameters so that they can be reviewed, and you can determine whether you want to accept that change, whether you want to reject it, or set it for enforcement, which means you want to reset the value in the control system so it matches what you came up with during rationalization. So this is an important step of the integrity process. Now, different control systems and different tools provide different ways of doing that. One example is DeltaV actually supports some behind-the-scenes auditing, so it doesn't require any OPC connectivity. It's a background task in the DeltaV system that will periodically, based on what you define, compare the alarm configuration that's running in the actual controller versus what's offline in the engineering configuration, and it will flag any discrepancies and present them to you as a report. So now we're reaching the end of our session here. So just to kind of tie it all together, we went through the 7 steps of the alarm management program. Benchmarking initially and establishing the goals of a program and creating the framework in the alarm philosophy document. We then talked about how to create a continuous improvement process with rationalization going into implementation and alarm response procedure development, followed by performance assessment to identify whether we're making things better or how we're making things better, and to identify new issues. We also talked about the need to sometimes do advanced alarming or alarm suppression as a different problem to address. Implementing this continuous improvement will certainly improve the effectiveness of the operator, because now we've gotten rid of many of their nuisance alarms. We've implemented alarm response procedures, training them on how to respond. So that will definitely make the alarm system a much more effective tool for them. That will also improve the plant safety. You can see also that as part of this program, we've documented, or we've given ourselves the ability to document and calculate metrics to show how we are changing the performance over time, hopefully improving it. And we can also see that, you know, once we clean up the alarm system and get it down to a manageable number, the ability to create that situation awareness factor for the operator might actually allow them to start to really improve the way things work. So significant benefits from following this kind of alarm management program. Now, one of the key takeaways that I mentioned earlier is certainly if you have a running control system or you're designing a system, find out what alarm functionality is available in your DCS so that you can figure out how to leverage it in the way that makes sense to you. The last thing I want to see happen is alarm management functionality is what I'll say is left on the table because people didn't know about it or didn't know how to use it. There's a lot of powerful alarm management capability that will help you solve these problems that we all have, these alarm management issues. So it's incumbent upon you to find out what's available and then figure out, get assistance, help you figure out how to best implement that within your control system. So on that note, we draw our session to a close. I appreciate everyone tuning in and supporting the exida webinars. Take a quick look to see whether there's any questions. I do not yet see any questions, but if you have any, now's a good time to enter them. We are about out of time, so I think we'll pass on answering the questions and we will do them as part of the follow-up. There were some good questions at the earlier session, so we'll combine all of them so everyone gets to see the answers. So again, I appreciate everyone tuning in, your support of the exida webinars, and I encourage you to check out more in the future, and also look at the webinars that we have online, the recorded webinars from previous sessions, and hopefully you'll gain some benefit from that. So again, thank you, and have a good day.